Let's look at this question. No, here. This question. Problem 3. A grade beam AB, you can see that the beam is A, B, and you can see the forces here linearly increasing until it reach constant, and then WA is here. There is a reaction here, RR, 5.4, 3.6, and then 6 kip, 4 kip, and then force P, and all these are the dimension. A grade beam AB support 3 concentrated loads and rest on soil. Of course, you can see the soil. The soil here is in the ground. The soil will have a force, increasing linearly and then constant. Okay, on top of the large rock. The soil exerts an upward distributed load, and the rock exerts a concentrated load RR. So there is, you can see here there is a load reaction from the rock. This is the beam. The whole thing here is soil pushing. There's the pushing force up, and there's a rock reaction of the rock, as shown. Knowing that WB is 0.4 WA, so the WB here is 0.4 times WA. Determine the largest value P for which the beam is in equilibrium and the corresponding WA. So he wants to find out the large P, determine the larger P to have it in equilibrium, and he wants to find WA. Let's rearrange the equation and let's put everything together. Okay. Remember, we have a reaction here, reaction of the rock. And we have 6 kip, and we have the dimension 1.5, and you have 4.5 kip, and you have the force P. And let's go and see this one. From the RR, you can see here there is a rectangular distributed load. And this rectangular distributed load is 3.6, okay, times the distance. Oh no, not 3.6. WA is the thickness of the load times 3.6. And that's going to be in the center of 3.6. See, 3.6 is 1.5 plus 0.3, that's 1.8. So the force in the rectangle going to be in the center, and it's going to be WA 3.6. 3.6 WA in the center. So this is R1, as I said, 1.8 in the center, and 1.8 from here. And let's look at the other one. The other one here, you could see that this is a rectangular and a triangle. So there is two things. A rectangular, it is WB times 5.4. And that's going to be in the center, which is 2.5, 2.7. 5.4 divided by 2, 2.7. 2.7 from here and 2.7 from here. So this is 2.7, this one. And for the rectangular, and of course 2.7 from here, you have to take it like this. 2.7 from there plus 3.6, 7 and 6, 13, 3, 6.3. So you can see it's 6.3, and this is the rectangular. The triangle The triangle, it's 0 here, and it is WA minus WB. You can see it. WA, WB here, and the whole thing is WA. So this is WA minus WB times 5.4 times half, because it's a triangle. Okay? And should be 1/3 from the base. 1/3 from the base, and the base is 5.4. So 5.4 over a third plus 3.6. And that's going to be 5.4. So these are the forces. Now we should take summation of forces at Y to sum up everything and make them all equilibrium. Because we know R1 is 3.6 A1, and we know R2 1/2 5.4 times 0.6 W1, and we know R2 and R3. So we know R1, R2, R3. Now we should take summation of moment at A. Summation of moment at A. Remember, we have a force from here, force from there, force from here, which is RA, RR is unknown, force from here, and force B. And we're going to take moment at this point. So 6 kip gonna be negative times 1.5. R1 gonna push it that way, positive times 1.8. And then RR, if summation moment at this point, RR positive times 3.6. R2 positive, and that's 5.4. R3 times 6.3 positive. 4.5 negative times 6. And then P, it is negative. P is 1.2, 5.7, 7.2. That's the total distance. Okay? That's summation moment at A. So you'll end up with 28.836 WA plus 3.6 RR minus 7.2 B equal 36. That's equation number 1. We have 3 unknowns. Let's do summation of forces at the Y. You have them. Of course, you have everything. So negative, 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 plus, 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 plus. So we'll put this equation in the Y, and you should rearrange everything and add up the WAs and add up the constant. You'll end up with an equation like this. Remember, here are WA, and P. These are 3 unknowns and 2 equations. We need another equation. Let's do summation of forces at X. There's nothing in the X to take. But if you want to have a maximum value of B, RR has to be 0. So to have the maximum largest value of B, a force, RR has to be equal to 0, the reaction of the rock. So you're going to find the reaction of the rock equal to 0. Now you'll have 2 unknowns and 2 equations. From solving, you could get WA and B, and that's what they want. I think they want WA. Yes, he want WA and he want B. So for the maximum B, you have to make RR equal to 0. Thank you.